Welcome to EPG Pathshala. Now, having spent a few modules looking at Poisson regression, in this module we should look at quasi-Poisson regression. Now, the name is rather intriguing and it comes from the fact that we shall use a technique called quasi-likelihood. This is a technique due to Wedderburn, and it is slightly different from likelihood-based estimation in the sense that we do not exactly specify a likelihood, but rather we specify the mean and the variance function. So by the variance function, we specify how the variance varies in relation to the mean, and using these two, we are able to construct something called a quasi-likelihood function. This is a function which is not quite the likelihood, but has several key properties which are identical to those of the likelihood. By key properties, I mean some properties which basically guarantee the asymptotic behavior of the likelihood, and hence the quasi-likelihood function behaves a lot like the traditional likelihood, and we can maximize it to get maximum quasi-likelihood estimators. We shall do this in the context of Poisson data. The reason why we might wish to use a quasi-Poisson model rather than a Poisson model is the situation where we have either over-dispersion or under-dispersion. So as you know, in this situation, we do not have V mu equal to mu, but instead V mu greater than mu or less than mu. This can be handled by introducing an additional scale parameter theta and specifying V mu equal to theta mu, where theta is allowed to be estimated from the data. Hence the requirement for a quasi-likelihood based technique. Now, we really do not know any parametric model for count data which would allow the variance to be equal to some function theta mu, where theta mu can be estimated from the data, and this is the utility of quasi-likelihood based estimation for the case when we have a count variable. We shall illustrate this using a data set on the number of patient visits, and this is based on our vignette due to Xylus. Learning objectives for this module. We shall first define the concept of over-dispersion as also the related concept of under-dispersion. We shall look at some examples and see why such a phenomenon arises. Next, we shall move on specifically to the quasi-Poisson model and see how this arises as a special case of quasi-likelihood techniques. We shall look briefly at the quasi-likelihood techniques which lead to estimates of the regression parameters but not of the scale parameter. So our final learning objective is to consider estimation of the scale parameter. The quasi-Poisson model. First, let us define the phenomenon of over-dispersion. Over-dispersion is specified by the situation where the nominal variance exceeds the model-based variance. So here we have two concepts of variance for an outcome variable, the nominal variance and the model-based variance. So say for example we have count data. By nominal variance we mean the empirical variance obtained by taking 1 over n minus 1 summation yi minus y bar square. So say we have one categorical predictor, then in this case we could look at this variance within each category, and this would give us the nominal variances. We also have a model-based variance, and you know that when the Poisson model holds, the Poisson model being the most common model for count data, the mean is assumed to be equal to the variance. So say we have a situation where we have a single categorical predictor, we find the empirical variances within each category, and we find that the empirical variance exceeds the mean. So this is the situation of over-dispersion, which for counts means that the variance is greater than the mean. So just as we can define overdispersion, we can also define a phenomenon called underdispersion, and this would mean that the variance is less than the mean, or that the nominal variance is less than the model-based variance. So in general, disagreement between the nominal variance and model-based variance is a situation where we have overdispersion or underdispersion, and we shall see that it is in this situation where quasi-Poisson likelihood turns out to be a useful alternative for modeling count data. So examples of situations where we might have overdispersion. The first example is where the entire population is not really a set of homogeneous individuals, but a set of clustered units. So for example, say we are looking at the number of people with a certain blood type, and rather than going to a completely random sample, we first categorize the population into families and look at the number within families. Now, of course, we would expect to see similarities within a family, so the family here serves as a cluster, and if we write down a general model formulation using random effects, we will see that in this case, we can expect a variance which is greater than the mean. The second situation is where we have subject-specific effects. We shall look at this in more detail in the modules on longitudinal data and also in subsequent modules in this paper. The third is where the number of observations is not fixed by design but is random. Now, these are all situations where it is possible to model parametrically the nature of the overdispersion. However, a very large class of models where overdispersion can arise is for observational data in the situation where we have model misspecifications. Very commonly, the model misspecification could be an omitted covariate. Now, since in any practical situation we would not really know the relevant covariate, we would not be able to correct for this, and thus it is important to have a general body of methods which allow for the phenomenon of overdispersion. So, two examples where overdispersion can arise. The first relates to the case where we have the conditional and the marginal mean. So, note that the marginal mean of y is given by expectation of expectation y given mu. The variance, the unconditional variance of y is given by expectation of variance y given mu plus variance of expectation y given mu, which is equal to expectation of mu plus variance of mu if we assume that the assumption of mean equal to variance holds conditionally. Now, as this is equal to theta plus variance mu, where theta is expectation of mu, it is greater than theta, and thus if the assumption of a common mean and variance holds conditionally, it is not guaranteed that the same assumption will hold when we apply it to the marginal distribution of y. The second relates to the case where we have a count, but the rate parameter for the count itself is not fixed parameter but has a random distribution across the population, which is specified by the gamma distribution. So here we have f lambda k mu equal to k by mu to the power k by gamma k exponential minus k lambda by mu lambda to the power k minus 1 lambda greater than equal to 0. So lambda here is the rate parameter, and it has a gamma distribution with parameters k and mu. In this case, p of y given k and mu is gamma of y plus k by gamma k gamma y plus 1, k by mu plus k to the power k into 1 minus k by mu plus k to the power y for y equal to 0, 1, 2, so on. It is possible to show that for this distribution, expectation of y is equal to mu, and variance of y is mu plus mu square by k, which is greater than mu, and hence we have another situation where overdispersion arises. An application in R on the physician visit data which is taken from the R vignette by Xylus. On the x-axis here, we are looking at the number of physician office visits, and on the y-axis, the corresponding frequencies. Note that the number of physician office visits is a count. From here, we can see that this count is rather skewed, and when we look at further empirical plots of this data, so here, for example, in the right panel, we have found box plots of the data by category, and we can see by looking at the box plots that there is variability in the mean and the variance, and that it does not appear that the mean and the variance are equal within each category. However, here we have conducted the first step by fitting a usual Poisson regression using the GLM command in R. So we fit GLM of the number of physician visits and the covariates, and we say family equal to Poisson. So this fits the usual log linear Poisson regression model. We can run the summary command on the FMPOIS object, and along with the standard output, which is the estimate, standard error, z values, p values, and so on, we see that there is a significant line of code which says that the dispersion parameter for the Poisson family is taken to be 1. Now, it is possible to partially adjust for the phenomenon of over-dispersion by using robust variance estimators. So, robust variance estimators are obtained using a procedure called sandwich variance estimation, and this can be done by running the coef test function with the option vcov equal to sandwich. So, running this will return the table given on this slide. You can compare the estimates and standard errors to the previous set and see that the estimates are as before, but the standard errors are now changed. It is a good exercise for you to study further the exact nature of the change. Our next option is to fit quasi-Poisson regression. So this can be done quite easily within the GLM framework. So here we have created an R object fm_qPOIS. As before, this is done using the GLM command. The first argument to this is outcome tilde formula. In this case, this is all the covariates in the data set. As before, I say data equal to dt. The only change is that I now say family equal to quasi-Poisson rather than family equal to Poisson. When I do a summary of the quasi-Poisson object, I get the usual estimates: the coefficient, the standard error, t values, and p values. There is, however, one line of difference which says that the dispersion parameter is no longer 1, but rather there is a line saying that dispersion parameter for the quasi-Poisson family was taken to be 6.706254. Now recall that on the first slide I had said that fitting a quasi-Poisson model would assume that if the mean is given by mu, then the variance is given not by mu but by a function theta mu, where we allow theta to be estimated from the data. So that is what we have done using the quasi-Poisson option, and it turns out that for this data set, theta is equal to 6.7, which of course is considerably larger than 1, and hence it appears that there is substantial over-dispersion in the data. As before, we get the null deviance and the residual deviance. However, fitting a quasi-Poisson option does not return the Akaike information criterion, and the reason for this is that when we fit a quasi-Poisson model, we are assuming that there is a relationship between the variance and the mean without specifying a likelihood. So in the absence of a likelihood, we are not able to define the Akaike information criterion. Another alternative which we could have fitted to the model is negative binomial regression. This can be done using the R function glm.nb. The rest of the syntax being as before. We can run a summary of the object, and the output looks very similar to that given on the previous slide. In fact, here is a comparison of the regression estimates obtained from the Poisson fit, the quasi-Poisson fit, and the negative binomial regression. Now recall from my previous slide that negative binomial regression also allows for overdispersion, except that it specifies a particular nature of the overdispersion. You can compare the coefficients and see that they generally tend to be similar. An interesting exercise for you is to compare the standard errors from each of these fits. So what is it that we really did using the Quasi-Poisson family? Let us look at the motivation. Now, if we have a model which is specified by a probability function f, and if we find the score equations under the model f are typically given by the form summation I equal to 1 to m si f theta m hat equal to 0. We are assuming here that we have observations on m independent subjects. SIF is obtained by taking the derivative of the log likelihood, assuming a distribution f. However, assume that the true nature of the distribution is not specified by f, but rather is given by some other function, some other probability distribution, which is given by g. It is possible to show that theta m hat will tend to some theta star such that the expectation under g summation I 1 to m SIF theta star is equal to 0. That is some value of theta star which satisfies this condition, and further that the estimated theta m hat obtained by solving the score equations for f, even though the true distribution of the data is not specified by f, can be shown to have an asymptotically normal distribution with root m theta m hat minus theta star tending into normality with mean 0 and A inverse B A inverse variance covariance matrix for suitably defined A and B. The quasi likelihood stems from this assumption. The quasi likelihood was introduced by Wedderburn in 1974. We defined the quasi score function given by S beta summation 1 to m Si beta summation I equal to 1 to m del mu del beta transpose variance inverse yi beta phi yi minus mu I beta equal to 0. Now this is a score function which corresponds to a likelihood obtained by integrating this score function given by q of mu y equal to summation I 1 to m integral yi to mu y yi minus t by a phi vt dt. Note that construction of the quasi likelihood does not require us to specify any likelihood, but only requires us to specify the variance function v of t. So in any situation where we are able to specify vt, instead of going for likelihood based estimation, we can construct the quasi likelihood and the score functions obtained by pretending that the distribution of the data is given by q, even if it is not, and apply the properties in the previous slide to get the asymptotic distribution of the regression coefficients. So to repeat again, no distributional assumptions are made. The only assumptions are expectation yi equal to mu I of beta and variance yi equal to vi is some function a phi into v of mu I. Key properties of the quasi-likelihood score function are expectation si equal to 0, variance of si is minus expectation del si del mu I. We know that these properties hold for the normal score function, and they also guarantee the asymptotic behavior of the quasi-likelihood function, and that it is similar to the asymptotic behavior of the usual score function. Quasi-likelihood estimation returns us estimates of the regression coefficients, but it does not give us an estimator of the scale parameter. The scale parameter is used obtaining a method of moments type estimator given by a phi hat equal to 1 over m minus p into a Pearsonian chi-square type variable, summation I equal to 1 to m yi minus mu I hat square by V of mu I hat. This is equal to the chi-square of fit obtained by the sum squared Poissonian residuals divided by m minus p, p being the number of covariates. In this module, we have introduced the quasi-Poisson model. A key assumption of the Poisson probability distribution is that the mean is equal to the variance. However, from an observational perspective, there is no necessity that for any count variable, the mean should necessarily be equal to the variance. And to begin with, we have seen some situations where the variance is either larger than or less than the mean. One example is clustered data. Another example could be where the Poisson rate parameter is not a fixed parameter but itself can be assumed to have a distribution across the population. In each case, this has led to a phenomenon called overdispersion. There are several ways to address the overdispersion problem. A simple way being to use the negative binomial regression model. However, the negative binomial regression framework assumes a specific nature of the overdispersion, and a more general formulation is possible using quasi-likelihood estimation. Quasi-likelihood technique is due to Wedderburn, and it involves specifying not the likelihood but the variance as a function of the mean. Using this variance function, we are able to construct a function called the quasi-likelihood, and it has been shown that maximizing the score functions from the quasi-likelihood can lead to estimators with desirable properties. So in the case of quasi-Poisson regression, we specify V mu equal to theta mu, where mu is the mean and theta is some overdispersion or underdispersion parameter which we do not specify but we estimate from the data. We construct the corresponding quasi-likelihood, and this leads to valid and robust estimators of the regression coefficients. However, it does not give us any estimate of theta, and for this it is necessary to use a method of moments estimator based on the Poissonian squared residual chi-squared. Thank you.